Hey everyone, welcome back to our week 12 of Graduate Statistics. We're working with linear regression, and this is the second problem we're going to explore today. Nature or nurture? In 1966, Cyril Burt published a paper called The Genetic Determination of Differences in Intelligence, a study of monozygotic twins reared apart. The data consists of IQ scores for an assumed random sample of 27 identical twins, one raised by foster parents and the other by the biological parents. So remember, they were reared apart, which means they were subjected to different nurturing, but they shared similar nature, if nature is defined here, I know, perhaps very narrowly, as similar genetic code. Because they are monozygotic twins, they have the exact same DNAs. And here is the relationship that was found when the IQ of the biological and the foster, between the IQs of biological and foster child. So the relationship is pretty strong. Right? So you can see how the dots are not very far apart from the line with a correlation coefficient of 0.88. And this is the output of the regression. Here we have the intercept, and here we have the estimate. That's the variability expected for the estimate, the t-value, and showing that there is actually more of, this is large enough to overcome the noise and be significantly different from zero, right? So here's the linear model. The predicted foster IQ equals 9.2076, which is the intercept, plus the slope, 0.914, bio IQ. So if I know the IQ of the biological twin, I can predict the IQ of the foster child, the foster brother or sister, using this equation. All right. And the slope tells us that for each unit increase in the IQ of the biological, the IQ of biological children, the IQ of foster child will increase by 0.90. All right. And the R square, just squaring the R value that we saw there, 0.8 something, we have the 0.78. So 78% of foster child IQ is explained by the IQ of the biological brother and sister, which means, I guess the extrapolation that they wanted to make is that is explained by their DNA alone, right? So a lot of the IQ is explained by DNA alone. So testing for the slope hypothesis, let's make that more concrete now, just like we did for the R. Is the explanatory variable a significant predictor of the response variable? So our null hypothesis is that beta 1, which is the slope in the population, equals 0, and the explanatory variable is not a significant predictor of the response variable. There's no relationship. The slope of the relationship is 0. And the alternative is that something is going on, that the slope of that relationship is different from 0. The explanatory variable is a significant predictor of the response variable, and the slope of the relationship is different from 0. Just like I said with R, we don't have a beta distribution. We use the t statistic as a way to test whether the value of slope that we are estimating is large enough for us to say that it's not likely under the null hypothesis. We have to compute a t statistic, and it's just the point estimate, the beta the b, which is the estimate of the beta, the slope we estimated, minus the null value, which is 0, divided by the variation, the standard error. And then we can compute the t statistic, and the degrees of freedom is the number of participants minus 2 as well. And we can check if that value is likely or not under the null hypothesis, looking at the distribution. All right? So the degrees of freedom is n minus 2 because we lose 1 degree of freedom for each parameter estimated. In linear regression, we estimate both beta 0 and beta 1, intercept and slope. So calculating the t statistic, if we have this table, it's kind of easy to do because here we have the estimate, which is 0.914 minus 0, divided by the standard error right there. So we get to the t value, and we look at the probability of finding a value of t or greater, given a t distribution with 25 degrees of freedom. And to get that probability, we know that it's very, very close to 0. It's less than 0.000, a bunch of zeros and 1, right? So we can say that it's very unlikely to observe this particular magnitude of t under the null hypothesis, so we dismiss the null hypothesis. You may be asking, if I run a correlation and I get an R estimate that's statistically different from 0, or it's very unlikely to see that magnitude of R under the null hypothesis that there is no correlation in the population, and I dismiss the null hypothesis, and I say that the two variables are correlated, why do I have to do it again here in regression to see if this particular predictor is reliably related to and contributing to the explanation of our dependent variable, here, the IQ of the foster sister, brother, sister. For simple regression, it's sort of redundant because if I find that the correlation between the IQ of biological and foster twins is statistically reliable, of course, when I look at whether or not the IQ of the biological twin is a significant predictor of the IQ of foster twin, it will say yes, because it's the only thing that could be explaining that correlation, right? It's the only thing in this model. However, it's important to introduce you to this because next class we'll do multiple regression, where you can see potentially that a model as a whole, like with a model with multiple predictors, has like a significant R squared. It's explaining well the dependent variable, but not all of the predictors are important. So we have to look at the overall fit of the model, which we can do looking at the R squared and the R. But in this case, I'm teaching you to look specifically for the significance of the predictor because this will become extremely important when we move on to multiple regression, okay? So variability partitioning. So far, we've been using t-test as a way to evaluate the strength of the evidence for a hypothesis test for the slope of the relationship between x and y, and to estimate whether the R coefficient is significant. But we can always do that by assessing and considering the variability in y explained by x compared to the unexplained variability, using an ANOVA, using an F distribution. Instead of estimating t from R and R squared, we can estimate F instead. It is possible to do so. And the logic is exactly the logic of ANOVA. We have a total variability in, say, the IQ of foster children or percent poverty, and we want to know how much of that variability is explained by our predictor. In the first example, percent of high school graduates. In the second example, the IQ of the biological child, biological sibling. And you have the unexplained variability that's not explained by predictors in the model. So you can do an F test for assessing the hypothesis as well. And I'm not saying this to confuse you. I'm saying this because when you run a regression, you will see a value of F, a value of T, so you know where this is coming from. You can both test hypothesis by transforming your statistical estimates of beta, of rho into t values and checking in the t distribution, or you can transform those in an F score and check that in an F distribution. So if after you estimate your model, you ask for the ANOVA output, you'll see that the kind of table that you've seen when we ran ANOVAs before, right? You have the variance explained by the sums of squares, which is the variance explained by your predictor, what's unexplained, and the total. And it's calculated in the exact same way as before, right? The total variability is the total deviation of all of the scores of your dependent variable from the mean, from the overall mean. The unexplained variability here is just the residuals that you learned how to compute, are the deviations of the actual value of the dependent variable and the predicted value from the model. And the explained variability is just this minus this. So you have that. So you can literally, just as before, having this, you have the degrees of freedom. And from the degrees of freedom, you can compute the mean deviations, right? You have this divided by that, which is this divided by that is this. So you can compute the F value as the ratio of these two and check this value against the F distribution to see if it's large enough for us to dismiss the null hypothesis that the biological IQ is not predictive. You know, the beta is 0 for that particular variable. All right. So I'll come back with our last example, doing regression with categorical variables. That will be the last video for us to finish up and go to the lab piece of this class. See you then. Bye-bye.